Good morning, good afternoon, good evening, whatever the case may be. We are back and better than ever indeed. And today, along with earth, wind, and fire, we are indeed grooving tonight with quantiles or K values, part one. There might not be a part two. We'll see. I'm not sure. But it's part one nevertheless. Let's get to it, shall we? Consider a population of crabs where the length of a shell, the random variable x millimeters, is normally distributed with a mean of 70 millimeters and standard deviation 10 millimeters. A biologist wants to protect the population by allowing only the largest 5% of crabs to be harvested. And this makes sense because we don't want to do away with a fine population of crabs. He therefore asked the question, 95% of the crabs have lengths less than what? Well, that what is what a K value is, or a quantile, okay? So we need to know we can figure this out using this nice little equation here. The probability that the random variable x is less than or equal to k is equal to 0.95, okay? So what's happening here is we're given the probability and we're asked to calculate the corresponding measurement. In other words, this is 95% of the area under the curve, the normally distributed curve, is covered, and we want to find what value of k corresponds to that. So let's move forward, shall we? Just a real straightforward example. Let's say that we have the normally distributed variable x. The random variable x is normally distributed with a mean of 23.6, standard deviation 3.1. Find k, for which the probability that the random variable x is less than k is indeed 0.95. Okay? So a sketch always helps. Sketch always helps. So we have a mean of 23.6, we have a standard deviation of 3.1, and we're looking for this value of k, where for that value 95% of the area of the curve is covered. And we do that very simply with our calculator, okay? And we use what is called the inverse normal variable, because we're not finding the probability, we're finding the corresponding value. So we go to probability, distributions, and inverse normal. There we go. It's so simple, and we're looking for a coverage of 95% of the area, so 0.95. The mean is 23.6 if you wrote that down, and the standard deviation is 3.1, and we click and kapow. So the corresponding length would be what? To 3 sig figs, 28, or the corresponding value, sorry, would be 28.7. So the value of k would be, let me click on the pen there, and that would be k is approximately equal to 20, sorry about the messiness here, my pen's not working well, 28.7. Okay, very simple, very easy. Next example. If z is the standard normal distribution, find k such that the probability that the standard normal variable is greater than k is equal to 0.73. So this is very, very important here. The little distinction here, the greater than, okay, that z is greater than k is equal to 0.73. Interpret your result, okay? So again, the curve is the big dealio here. Got to know what we're looking for. So the greater than is the key here, yes? It's to the right of the curve. So what you also have to think when you're going to use your calculator here is that if the probability that the standard normal variable z is greater than k is equal to 0.73, then the probability that the standard normal variable z is less than or equal to k, in other words, this guy here would be 100 minus 73, or 0.27. Okay. Also, we have to realize it's standard normal. If it's standard normal distribution, then I know that the mean is 0 and the standard deviation sigma is equal to 1. Okay. So when we use our calculator, we're going to use this value. Okay, we're going to use this value. Whenever it's greater than, you want to do the area to the left of the curve. Okay, when you're doing inverse normal. That's just for inverse normal. That's how our calculator interprets it. Okay, so menu, probability, distributions, inverse normal. Okay, we need our area to be 0.27. And the default mode is for standard normal, which is a mean of 0 and standard deviation of 1. So all we need is the percent area that we need. Kaboom, we get negative 0.612. Okay, so go back here. So that would be k is approximately equal to negative 0.612. Okay. So that means for 73% of the values, the scores to be above 0.73, we're looking at a value of negative 0.612. Okay. This is going to be, this is part 1. A university professor determines that no more than 80% of this year's history candidates should pass the final examination. That's kind of harsh, isn't it? What if everybody gets, 90% or above on the exam? Anyway, not for us to decide. I won't judge. The examination results were approximately normally distributed, with mean 62 and standard deviation 13. Find the lowest score necessary to pass the exam. Okay, so what are we talking about here? Always sketch the curve. We're looking for, we had a mean of 62, and these poor folks are going to fail. They are going to fail. Okay, so what do we know here? We know that the random variable x is normally distributed, and we have a mean of 62 and a standard deviation of 13. Okay, so we're trying to find the probability that the random variable x is greater than or equal to k is equal to 80% for an 80% passing rate. Okay, which in turn implies, or is the same as, the probability that the random variable x is less than k, that probability is equal to 0.2. So we were looking for this particular score. Okay. So here we go, back to our calculator. Inverse normal. I guess I can go here and just copy it. Okay. And so the area that we're looking for is 0.2. So I'll just get rid of that 7. And then the mean was on the test score was 62 with a standard deviation of 13. Kapalza, so the lowest passing score, let's see, 51.1. Okay, so let's write that down. I better remember to tutor Michael tomorrow, huh? We'll save that for tomorrow morning. Okay, so K is approximately equal to 51.1. Okay, but we know that scores don't work that way, so if they're going to pass, if we want the 80%, we can't go down to 51 because it has to be above 51. So the passing grade, The lowest passing grade would be a 52%. Okay, that is it for part one. We will regroup and do part two. Until then, let's see how our good friends Earth, Wind, and Fire are doing, because, as you know, I have done all the damage I can do here, and I am out!